Today we're going to talk about absolute extrema and how to find them. Absolute extrema. Extrema is the plural of extremum, which means either a maximum or a minimum. So this is finding the absolute maximum value or the absolute minimum value of a function. Where by maximum minimum I mean the greatest or the lowest y value of the values of the function. These are a little bit easier to find and identify than the relative or the local extrema, which we're going to talk about a little bit later. But for the absolute extrema, I'm going to say easier to identify than the locals. The absolutes are a little bit easier. But one sort of technicality is that oftentimes there are no absolute extrema, but often they don't exist. And because of this, we're going to sort of focus our attention slightly differently than usual. So here's an example. You don't have to look too hard to make an example where absolute extrema do not exist. How about just like a line like this? This function, the line, has no absolute minimum or absolute maximum because it just goes up forever as you go to the right, and it goes down forever as you go to the left. So this one has no... I tried to turn that off. And I got excited because I saw a little thing popped up on my phone, and I was about to say, oh, I got an email, but I didn't hear it. And then I heard it. It's been one of those days. I forgot to wash my hair when I took a shower this morning. So I had to get in again. And then, for some reason, I'm not entirely sure that I actually forgot the first time around. So now I feel stupid about, like, even worse than, yeah. It doesn't really make a big difference for me, I don't think. But anyway, so this thing, what I was saying, this one right here has no absolute maximum or minimum because it just goes up forever to the right and it goes down forever to the left. So there is no like top value or bottom value. But the discussion of absolute extrema is typically done, so for this reason, because there oftentimes are no absolute minimum or maximum values, we typically restrict our attention, I will say, but if we focus only on a closed interval in the domain, then actually it would have an absolute minimum or maximum if we only consider a closed interval. So then it does have like a highest value and a lowest value. It does have absolute extrema. So what I mean by that is like draw the same function, but I'm only going to care about the values over a closed interval, like so let's say this closed interval right here, and we only look at these values right here. We just disregard the rest of the function. All right. Among these values right here, there is an absolute maximum, the one up there, the top one on the right, and there is also an absolute minimum, the bottom one on the left. All right. If we consider only a closed interval in the domain, then it does have absolute extrema. And in fact, this is not just a property of the line. This is true of any continuous function. Here's another function, something like this. Right? This one overall does not have any absolute maximum or minimum, but if you focus only on a closed interval, and it could be anywhere, maybe this interval from here to here, say, that means I only take from this point and this point, and I only look at this part of the function. That one does have an absolute maximum and minimum value, just among the blue part. I suppose the absolute maximum would be there, and the absolute minimum would be there. Absolute maximum, absolute minimum, right? if I only focus on that closed interval, then it does have an absolute maximum and an absolute minimum. All right? And there's a theorem which says this. We're not going to talk about the proof of this theorem, but I'm going to write it down at least. This is one of the big sort of theorems. There are several big important theorems from calculus which have the word value in them. We've talked about the intermediate value theorem was one of these. This one is called the extreme value theorem. Theorem. Remember, extreme value just means either maximum or minimum. And it says, basically what I just said, it says if f is continuous, on a closed interval, so if we only consider the closed interval as its domain, I'll call it a to b, then f of x has an absolute maximum and an absolute minimum on the interval a to b. So if I only consider the closed interval, and it has to be a closed interval for this to work. I'll show you in a moment why it doesn't work if it's an open interval, or like half open, half closed. It doesn't necessarily work. All right, this is called the extreme value theorem. If you use the closed interval, then it has to have a minimum and a maximum value in there. And it has to be a continuous function also. All right, let me just say the interval must be closed. If you use an open interval, for example, I could do even with that same line that I've been drawing over and over again, but using an open interval as my blue thing, that means I'm going to go, say, from here to here. The function would go like this, right? But it would exclude the top and the bottom values, all right? And I hope you agree with me when I say, so those are like empty circles there. That means the blue part, at least, doesn't actually reach the top value. It goes like all the way up to it, but not including the top value. So actually this blue function that I've drawn here, this piece of a function, does not have a maximum value. You might say, isn't that one up there the maximum? Well, it doesn't reach that value. It gets super close to it, but it never actually reaches that value. So there is no one specific y value which is bigger than all the others. All right, this is a little strange but true. All right. So the interval must be closed. If you use an open interval, then actually you don't get necessarily an absolute maximum and an absolute minimum. And also the function must be continuous. Let me just show you why the continuity matters. Here's an example of a function which is not continuous. Even if I look on a closed interval, let's say from here to here, if the function does something like this, on this closed interval, I'm doing. Even if I focus just like on this interval here, so the blue part is really all of it. Everything that I drew here counts as the blue part. The issue is this is not continuous because of that jumpity jump in the middle, and you can also tell this one does not have an absolute maximum value because that's an empty circle there. So it does approach that value, but it doesn't actually hit that top value there, and there is no other specific y value here which is greater than all the other y values. All right, so the interval must be closed. Also, the function must be continuous. That's what I'm trying to impress on you. Right? Because if it's not continuous, then weird things can happen. If the interval is not closed, then weird things can happen. But if it's continuous and the interval is closed, then your function must automatically have an absolute maximum and a minimum on the interval. That's the extreme value theorem, the second of our value theorems. We're going to talk about another one next time. All right, let's look at just some very simple examples. I want to see if we can discern some kind of pattern about, remember what I want to talk today is how do you find the absolute extrema? It's easy just by looking at a graph of the function, but ideally I want to be able to just tell you an equation with a closed interval and say find me the absolute maximum and minimum on that closed interval. So something I would like you to notice, if I consider only like a piece of a function, you know, it might look something like that, right? A function, but only a piece of it on a closed interval. You will notice in this picture here, the maximum is right there. This is the absolute maximum. Where's the absolute minimum here? The smallest y value that you can see. I think everybody's looking at it. Tell me where. Yeah, it's the endpoint on the left side. This point right there, that's the absolute minimum. Right? How about, here's another example, something like maybe a function like this. In this case, the absolute maximum would be there. And the absolute minimum would be there, right? Or maybe something like, here's something quite strange, could be maybe a function that has like a pointy point in it, like that. All right. In this case, the pointy point is actually the absolute maximum. And the minimum, I guess, would be this point on the left. All right. I just want to draw a bunch of different pictures because there's actually sort of a pattern or a categorization that you can come up with for, as far as the picture goes, where could the absolute extrema possibly be? And they can't appear just anywhere. You can say something, in fact, in terms of the slopes of the original curve, where they could be. Anybody have a thought about this? Maybe you've seen this before. I don't know. Where could the absolute max and min appear? Something having to do with the slopes, perhaps? Yeah? Yeah. Yeah, he says when the slopes equal 0 or on the endpoint. So sometimes they occur on the end, like this one or this one. But they can also occur at these sort of mountain peaks or valley points. And those are where the slopes are 0, or here. I didn't put a nice little dot on it. All right? So let me just say here, I will notice the absolute extrema occur. There's a couple of possibilities, right? They could occur at the endpoints. At the endpoints. I don't mean they always occur at the endpoints. I just mean that it might be on the endpoints. Or it might be at some point, he said, where f prime of x equals 0. Right? That would be like the mountain peaks and the valley points. Like this one right here. Or actually there's a third option. Can anybody say? There's actually one other case here in which the absolute maximum occurred at some other point that was not an endpoint and also not where the derivative was 0. Yeah? Yeah, like right here. This point here has, the derivative is not 0 there because it's like a pointy point. Actually, the derivative there does not exist. It's not differentiable at that point. So I'm going to say, or at some point where f prime of x does not exist, right? And those really are the only options. If you're talking about absolute extrema of a function on a closed interval, it can only occur either on the ends or at some point where the derivative is 0 or does not exist, right? This we kind of saw, this is related to my parable about the highest point in Connecticut. The highest point in Connecticut, we would expect it to be at one of the mountain peaks, but actually it's not. It's on the end, right? It's on the border. So the highest point in Connecticut is an absolute extremum, which falls into the first category. It's at the end point. Now, actually, the state of Connecticut is not like a line and a function. It's more like a two-dimensional thing which has heights to it. There is like a higher dimensional version of the of this, everything that I'm talking about, that you will eventually learn about in Calc 3, multivariable calculus. But anyway, there's some cute language for this right here. These things, the values or the points where the derivative is 0 or does not exist, there's a name for that. These are called critical numbers. To kind of an umbrella term for those last two categories. So I'll just write the definition of that. A critical number of some function f is some point C in the domain where either f prime of C equals 0 or f prime of C does not exist. All right. Those, if either of those things is true, it's called a critical number. And the reason we care is that the critical numbers are where the absolute extrema might be, right? They don't exist. Such a point is not always the absolute maximum or the minimum because it might be on the end, all right? But these are possible locations for the absolute extrema. And so there's our method for finding them is basically find all such points and then just check the y values and see which one is the biggest and see which one is the smallest. And there's a name for this method. I actually had never heard this method given a name, but in our textbook they have a name for it. So I'm going to say to find the absolute extrema. This is called the closed interval method. The closed interval method is what they call this in the book. So this only works when f is continuous on the closed interval. On the closed interval, let's say from A to B, then all you got to do is you just check all the y values at the endpoints and also at every critical point. So we check all the values of f of x at any critical numbers and also at the endpoints. Because those are the only possible locations where the maximum and the minimum might be. And then among all of those, you just choose the biggest of those numbers, and that one is the maximum, and it must be the maximum of the whole function. And you also choose the smallest. So the biggest and smallest of these are the absolute minimum and maximum. All right, and I just want to try some examples here. Any thoughts about the basic strategy? It is not, sorry about that, I really don't know how to turn that off. There's not a whole lot to it. You just got to find the critical numbers and plug a bunch of values into the function and pick the largest and the smallest. All right, let's see if we can do it. I got a simple example and then one that's a little harder, and I got one for you to try. How about find the absolute extrema for this function? F of x equals 2x cubed minus 18x squared minus 6 on the closed interval minus 1 to 10. All right. In such a problem, you will always be told the function and also a particular closed interval. Because if you don't restrict it to a closed interval, then there's no guarantee that there even is an answer to this question. And it becomes quite a bit harder if you don't know ahead of time that there is an absolute minimum and maximum. All right, anyway, what we have to do, we plug in all the interval endpoints and all the critical numbers into this function. So first I'm going to find the critical numbers. And then I'm just going to do a bunch of plugging in. Find the critical numbers. These would be specific points where f of x equals, where f prime of x equals 0 or f prime of x does not exist. So we might as well find the derivative first. F prime of x. This is easy enough function to take the derivative of. It should be 6x squared minus 36x, I think. right? That's the derivative. I want to know when the derivative equals 0, and also when the derivative does not exist. So first you just have to check those separately. First I will check when the derivative equals 0. So I set this equal to 0, and try to solve for x here. I would factor that, I guess. I think I can factor out 6x, and what remains is x minus 6. And then this, I get two solutions, right? X equals 0, x equals 6. So these are two critical numbers. Those are points when the derivative equals 0. We also need to check when the derivative does not exist. Now, usually, the examples that we're going to do, the derivative does always exist. But what you've got to do is look at this formula here, f prime of x, and ask yourself, are there any x values where this does not exist? And the answer in this example is, no, this always exists, right? This is a quadratic, so it looks like a parabola. There's no funny business. What you should be looking for in this step is something like, could you get 0 in a denominator or a negative number in a square root or something like that? But that's not possible in this example. So for the DNE step, I'm just going to say like a NA. There is no opportunity for this function to not exist. I'll just say f prime always exists, right? It doesn't have any 0 in the denominator points or any other kind of funny business which would cause the derivative to not exist at some point. Okay, so that means the only critical numbers are those two which we just found, x equals 0 and x equals 6 are the only critical numbers. All right, and remember our strategy is I plug these numbers, 0 and 6, and the endpoints into the original function, and then we just like choose the biggest and the smallest value. So we're going to plug in x equals 0, x equals 6. Those are the critical numbers. And also the two interval endpoints, which you'll have to look back what I've said. This is the only time when the interval matters for what you're doing. Minus 1 and 10. So x equals 0, 6, minus 1, x equals 10. And I'm going to plug them all into f of x. It's easy to get this confused. Make sure you are plugging into f of x, not f prime of x, right? F of x, the original function, not the derivative. So that would be, I'm just refreshing my memory here, 2x cubed minus 18x squared minus 6, right? This is the function that you have to plug these numbers into for the purpose of seeing which one is the biggest and which one is the smallest. And these numbers are a pain to do by hand. If I was giving this to you on a quiz or something, I would make the values easy enough to plug in without really working for it. But I use my calculator to do this. F of 0, actually that's easy enough to do. It's negative 6, right? If you just substitute x equals 0 in there, that's easy to do by hand. Basically, all the other ones are a pain to do. I'll just tell you what I got when I use my calculator. I got f of 6 equals negative 222. F of negative 1 is negative 26. And f of 10 is 194. All right. Remember what we're doing here. We're trying to find the absolute maximum and the absolute minimum. And those numbers, whatever they are, they have to be one of these four. And so you can just choose the absolute maximum, I guess, would have to be this last one, right? It's not any of the other ones. This last one is the biggest one. So this right here is the maximum. And the minimum would be this one, because it's, the most negative, right? So my final answer, if you wanted to write something nicely as your answer, I would say the absolute maximum is f of 10 equals 194, and the absolute minimum is f of 6 equals minus 222. All right? So I guess the absolute maximum in this example is on one of the endpoints, but the minimum is in the middle somewhere at 6. Yeah? Yeah, those are, so these are the critical numbers, These are the endpoints of the interval. And that's the only part in the whole problem when the interval matters at all. Yeah. All right. You can always kind of check your answer. I thought it might be fun to look at the graph of this just to see what it looks like. That's not it. So it's 2, I'm graphing the original function here, 2x cubed minus 18x squared minus 6. So this is the function here. It looks like that. And remember, we are only focusing on the interval from -1 to 10. So it's kind of like that much. I'm trying to just look at the interval from -1 to 10. And I hope you agree. I mean, you can see that we did it right. What of the values that you see on the screen right now, the absolute minimum is here at the bottom of this guy, which is at x equals 6. And the absolute maximum is up there, which is where x equals 10. Right? So I feel good about that. Any thoughts about that one? This is how we find the absolute maximum and the minimum without looking at the graph, right? That's really the whole trick. If I showed you the graph, it's very easy to just point at them. But we did it without looking at the graph. All right? Let's try a harder one. I got a harder one. I want a hard one. I went to Qdoba with my kids once. This is kind of a long time ago, when they were little. My daughter walked right up to the counter and said, I want a hard one. She meant like a hard taco. I thought that was funny. Okay, let's find the absolute extrema of this function. F of x equals x minus 2 sine x for this x in between 0 and 2 pi. All right? So I gave you the function. I didn't write it like a closed interval, but that other part is the closed interval, right? It says x is in the closed interval from 0 to 2 pi. So the other part there is a description of the closed interval, and the endpoints in this problem will be 0 and 2 pi. All right? The whole game really is to find the critical numbers and then plug everything into the function. So let's see if we can find the critical numbers. We should begin by taking the derivative and then set it equal to 0, and also ask ourselves about when the derivative does not exist. So, anybody want to say what's f prime of x here? Someone want to shout it out? You've probably already written it down on your paper. All right, thank you for shouting it out. 1 minus 2 cosine x is the derivative. I'm going to set this equal to 0. So we have to check, separately when f prime equals 0 and also when f prime does not exist. F prime equals 0 means 1 minus 2 cosine x equals 0. Solve this for x if you can. This would say 1 equals 2 cosine x, right? Cosine x equals a half. This is a little tricky. You got to be a trigonometry master, I guess. I hope that with some work you could work this out. You need, what are the x's which give you a cosine of 1/2? You could think about, if you have the values around the unit circle memorized, do you remember which one could give you cosine of something could be a half? Or if you think about it in terms of triangles, which is the way that I typically think about it, your triangles look like this, or this is like the angle. Cosine being a half is when the adjacent over the hypotenuse is a half, which would mean this is a 1 and this is a 2, right? The adjacent is the 1. The adjacent is a 1 and the hypotenuse is a 2. All right? Anyone recognize this picture? What is the angle there going to be? That's what the x would be, right? The cosine of x. In this picture, the cosine of x is 1/2. What angle makes this picture? It's not the 45 degree. If that was a root 2 up there, then it would be 45 degrees. In such a picture, you know, the other side would end up being root 3. Yeah, this is the 30, 60, 90 triangle, where in particular this x is the 60. So this is, and of course I'm going to write it as radians. This is pi over 3, 60 degrees, in other words. All right? Unfortunately, as everybody knows, this may be not the only x. Is that the only x that makes the cosine equal a half? There might be some other one elsewhere in the circle. Actually, there is another way the cosine could be a half, and that is if the angle goes like this, all the way down to another 30, 60, 90 triangle, right? This time that side would be negative, but as far as the cosine is concerned, that doesn't matter. So this is 60 degrees. If you count the angle negative, it would be an angle of negative 60 degrees, pi over 3, negative pi over 3. Or if you count it this way, which I am going to count it this way for reasons I will say in a moment, it would be 5 pi over 3. Right? All the way around is 2 pi, which would be 6 pi over 3. This is all the way around minus 60 degrees. All right. The reason I did that rather than just saying negative pi over 3 is because of this right here. We are only considering x's in this range, 0 to 2 pi. So it is true, actually, negative pi over 3 is a solution to this equation, but I disregard it because I am only considering x values in this region, 0 to 2 pi. All right, this one's a little tricky. Okay, so let me just say here, all other answers for x are outside the interval. And so we don't have to worry about them. Interval 0 to 2 pi, right? Ordinarily, when you solve equations like this, you get something like pi over 3 plus 2 pi n, where n is any number. You get infinitely many possible answers. This is not the case in this setting because we're only focused on this particular interval. All right? That's a little tricky. But anyway, that was the hard step. Now we can proceed. These are my two critical numbers, right? Pi over 3 and 5 pi over 3. We need to check those two numbers. Plus, we also check the interval endpoints, which are 0 and 2 pi. And that's all we got to do. So, sorry, can I just say very briefly? We also need to consider when f prime does not exist. This is part of finding the critical numbers. But again, in this problem, that's not an issue because cosine of x always exists. There's no opportunity for any kind of funny business. Now, if this were a tangent, then we would have to be concerned about some things because tangent has asymptotes in it, but cosine does not. So this also doesn't matter, right? There are no points where the derivative does not exist because cosine always exists. All right, now we can finish it off. So we need to plug in. I got to do f of pi over 3, f of 5 pi over 3. These are the two critical numbers, and then also the endpoints, f of 0 and f of 2 pi. All right, and we plug them all in. Make sure you plug into the original formula, which was x, what was it? X minus 2 sine x. Let's do it. This will be pi over 3 minus 2 sine of pi over 3. This is pi over 3 minus 2 sine of pi over 3. That's a 60 degrees. And conveniently, I already drew that triangle up here. It's this one. And the sine here would be the opposite over that hypotenuse. That's root 3 over 2. So that one is this 2 times root 3 over 2. That's the sine of pi over 3. This root 3 over 2. Because of that triangle there. Which I guess I could simplify this a little bit. Pi over 3 minus root 3. That's as far as I can simplify this by hand. Although you really, unfortunately, you do need to know what that number is because it's my intention to compare this number with the other answers that I get. And I have to be able to choose the biggest and the small. So actually at some point, you really just have to type this into your calculator. And I got negative 6.684 something something, right? You have to actually write out the decimals in order to compare the values with each other. Okay, let's keep it going. 5 pi over 3 now. So it's going to be 5 pi over 3 minus 2 sine 5 pi over 3. This is 5 pi over 3 minus 2. And the sine of that one is this triangle here. The sine will be opposite over hypotenuse again, negative root 3 over 2. So that's negative root 3 over 2, which is 5 pi over 3 minus, I guess plus root 3, right? The 2's cancel, and the minus make a plus. And this I plugged into my calculator and got 6.968, etc. All right. These other ones are a little easier to work out. F of 0 will be 0 minus 2 sine of 0. Anybody remember sine of 0? It's also 0. I saw someone give me the hand signal. Yeah, so this is just 0, right? Sine of 0 is 0. And f of 2 pi will be 2 pi minus 2 sine of 2 pi. Anybody remember sine of 2 pi? Also 0. Yes, you're still giving me the hand signals. So this will be 2 pi in the first part minus 0. So 2 pi. And for the purposes of comparing with the others, I happen to know 2 pi is something like 6.28. 3.14 is pi times 2. All right? That's about it, right? We just now compare these values, choose the biggest and the smallest. Yeah? Why? Up here, you mean? If it's equal to negative 1/2? I'm not sure you mean. Down, like down here? Did I? Yeah? Okay. I never understood the question. But if you're satisfied, I'm satisfied. All right, so just to finish, we choose the biggest and the smallest. It looks to me like this is going to be, that's the maximum, right? And the minimum is this one. It's the only negative value there. Okay, so in conclusion, the absolute maximum is f of 5 pi over 3 equals 6.968. And the absolute minimum is f of pi over 3 is minus 0.684, etc. There you go. Just like last time, if you like, you can graph the function and see if your answer makes sense. I don't think we need to do that, but these are always easy to check yourself if you have a grapher around. You can graph it and see. All right. Any thoughts about that one? That was harder. Just I think the harder part is this stuff here, right? Once you figure that out, it's not any different really from the other one. All right, I got some for you to try. Just one. How about this? Is not using the trigonometry stuff. Find the absolute extrema of this function. F of x equals x squared minus 4, the whole thing cubed, on this interval, minus 2 to 3. This one you can more or less do without using a calculator, although you might want to use a calculator on the very last step. All right, see what you think. We got about 10 more minutes. Feel free to talk to your friends as always. I hope you use the cane rule. Yeah, sure. I'll give you a couple more minutes and then we'll talk about it. All right, let's talk about them. We got 5 minutes. So this is the derivative. I hope you got that. That's the chain rule. Now, I saw a lot of different approaches to trying to simplify this. I think it does not really make sense to square this out, to expand this thing in the middle. You can, if you like, do 6x times x squared minus 4 squared. I don't know, that doesn't do much, but this is the derivative. Your next step would be to set this equal to 0 and solve for x. So f prime equals 0. I would say 6x, x squared minus 4 squared equals 0, right? Here I have two things which are multiplied together to give me 0, which means you can split it up as like 6x equals 0 or x squared minus 4 squared equals 0, right? From 6x equals 0, I get x equals 0, so that's a critical number. And then from x squared minus 4 squared equals 0, like here you can just ignore the square here, like square root on both sides. You get x squared minus 4 equals 0. This you could either move the 4 across and do the square root or factor it, x plus 2, x minus 2. And this gives me x equals minus 2, x equals 2. All right. So I hope you found 3 total critical numbers. 2, negative 2, and 0. So those are the 3 values I'm going to plug in, and then we also have to plug in the interval endpoints. In this case, the interval was minus 2 to 3. Now, it just by coincidence, one of the critical numbers is also the same as one of the endpoints. It don't matter. So I'm going to plug in f of 0, that was a critical number, f of minus 2, f of 2, and also f of 3. All right? These are all the things you got to plug. And I'm plugging into the original function. I will just refresh my memory, is x squared minus 4 cubed. So this one would be 0 minus 4 cubed. And here's where you might want to use a calculator. 4 cubed is 4 times 4 is 16, and then times 4 again is 64. So this, and it's going to be negative, because a negative number cubed is going to be a negative number. So you get negative 64 for plugging in 0. Plugging in negative 2 gives me minus 2 squared minus 4 cubed. That's 0 on the inside, so 0 cubed is 0. Positive 2, 2 squared minus 4 cubed. Again, this is 0. And then 3, this is something. 3 squared minus 4 cubed is 9 minus 4, that's 5 cubed, 125. Hope that's what you got. And so the minimum and the maximum are those two, the negative 64 and the 125. So I'll say absolute minimum is f of 0 is now minus 64, and the absolute maximum at f of 3 is 125. There you go. All right. I guess that'll do it. See you next time. Let me know if you have homework questions. I'd be happy to chat.